Okay, number 6 looks complicated, but it's a really good question to go over. You start with, they give you the region in the first quadrant bounded by the curves y equals x squared and a second curve y equals x. So I graphed those. That's what this green one is, y equals x, right? And the yellow one is y equals x squared. And this is the area that we have when we look at the cross section, and then it's rotated around the x-axis to form a solid. Now this is still on the exam because this is not integration or anything. We're not using cross sections or anything. They're just trying to get you to see what this looks like. So that would be the same thing. You would get the same piece down here, right? And so what you would get would be this donut, okay? And it would have a area, if this is the distance from one piece to the other, of x1, 2, and let's call this x2. So the radius there, it's perpendicular to the x-axis. So the area of this shaded figure, right, would be pi r squared. Area is pi r squared, but the r is going to be x squared, x2 squared. So it's like this. Well, I kind of put it together. Let me do it. It would be pi and then x2 squared minus x1 squared. Now, this is the x2, well wait, which one would be on the top? So the outer loop would be this y equals x. So this is the x2 graph, and this is the x1 graph. So substituting in what you have for x2 would be pi y squared, because I have x equals y, and minus pi, and instead I just factored out the pi first right here. And then y squared would be your other x, and that's squared. So this is the first r, this is the first r right here, and the second r right here. Okay, so we can factor the pi out, and we get y squared minus y to the fourth. So that is our function that we want to optimize. So we are going to take the derivative to set it equal to 0. So the derivative of this, keep the pi out, would be 2y minus 4y cubed. So here's number 4, like I put it over here. So this is 3, like this is 1, drawing it up. 2 is figuring out what we have here. 3, 4, here's 4. Taking the derivative and setting it equal to 0. There's a little cube up here you can't see. So to do that, if you divide by pi, it just goes away. So then I factored out a 2y, and I got 1 minus y squared. So I got y equals 0, and y is plus or minus 1 over the square root of 2. So this is a cubic right here, a cubic function. So if I want to use end behavior, I have 0 on my graph, and plus or minus 1 over the square root of 2. So that's negative 1 over the square root of 2 and 1 over the square root of 2. And this is a negative cubic function, so it would come down from the left, go through 0, and come back down. So I put my graph, there's a positive to a negative, so that's a maximization. And also this is not, the 0 is not feasible because it's a minimum. And then you go from a positive to a negative, get at positive 1 over the square root of 2. And but the thing is, when you put it back into the original equation, you have a square here and a 4 here, so you end up getting positive no matter what. So after you get these zeros, those are the places that it's maximized, not this one, plus or minus 1 over the square root of 2. You put it back into the original equation that you got over here for 3, which this is the best one, showing it right here. So this would be pi, and then I got 1 over the square root of 2 for one of my answers, squared, and then minus 1 over the square root of 2 to the 4th. And so you can see me working that out. That's 1/2 minus 1/4. So you get 1/4 pi. Okay, so the answer is 1/4 pi.